Welcome to the webinar, Are Critical Minerals Fueling or Failing the Future of Green Hydrogen? My name is Ian Reinhardt, Associate Research Director at Lux Research, and I will be moderating today's session. Presenting today is my colleague Abhirab Basu, Senior Analyst at Lux Research. Throughout the webinar, you can type any questions you have in the questions box on your screen. Time permitting, we will answer the ones that we can, but if your question does not get answered, please do not hesitate to mail it to questions@luxresearchinc.com, and we will respond. If at any point you experience technical difficulties, such as a frozen screen, simply try refreshing the browser and check that your internet connection is strong. Okay, let's jump into the presentation. Over to you, Abhirab.
Thanks, Ian. Hello, everyone. I'm Abhirab Basu. I'm a Senior Analyst at Lux Research. I work with Ian on the manufacturing team. And in more recent years, we've been looking at the challenge of sourcing critical minerals for the energy transition. In today's webinar, we'll explore whether those critical minerals and metals, are they fueling or they might fail the future promise of green hydrogen? But before we look ahead, I want to quickly glance back at a historical example of critical minerals. In the early 2010s, forecasts warned that phosphate rock, a key ingredient for fertilizers, could peak in production by mid-century. This was a problem. Phosphate is essential for food security. It's a finite resource, and the supply was concentrated in a handful of countries. As a result of these peak phosphate concerns, fertilizer prices spiked, food security became a political issue, and the world started scrambling for solutions. Spoiler alert, the forecasted mismatch between supply and demand didn't occur, largely because of innovation strategies to avoid it. So keep this peak phosphate example in your mind, and I'll come back to that later in my presentation. But just like phosphate, a critical mineral for food security that was at stake back then, today it's the energy transition and the role of green hydrogen in that transition that faces supply risks from key inputs. Instead of fertilizers, we're talking about critical minerals and metals for electrolyzers to power green hydrogen. So for today's webinar, I'm going to talk about the green hydrogen market, look at electrolyzer technologies. We'll map out the critical materials challenge for green hydrogen through our raw materials criticality framework. Using that framework, we'll devise innovation strategies that will help future-proof the green hydrogen deployments. So let's dive right into it. The IEA, the International Energy Agency's net zero scenario, calls for around 500 million tons of green hydrogen per year by 2050. That's about 5x of what we produce today, and majority of the hydrogen that we produce today comes from fossil fuels. That's a massive scale up. And by that 2050 timeline, you can see electrolyzers will be the workhorse of the hydrogen economy. Of all the upcoming planned hydrogen projects through the end of the decade, electrolyzer projects make up a lion's share. There are four main electrolyzer technologies: the incumbents, the alkaline water electrolyzer and proton exchange membrane water electrolyzer, and then emerging technologies like solid oxide water electrolysis and anion exchange membrane technology. As you can see from this chart, that we're way off the projected manufacturing capacity to come online by 2030 to stay on track for that net zero emission scenario. That means electrolyzer manufacturing capacity across these technologies has to grow up rapidly. So there's a big manufacturing challenge that we face today to meet that net zero scenario, even before we factor in other barriers to growth, and that's production economics. Today, the levelized cost of hydrogen for large-scale water electrolyzers, and this is an example out of Europe, is about 14 euros per kg. The largest cost driver, electricity contributing about a third of the cost. But electricity isn't the only problem. The cost of manufacturing, which is the capex and operation and maintenance costs of replacement of materials, is at least another third of the cost of producing low carbon hydrogen. So now layer in issues like shortages in raw material, highly concentrated supply chains, volatility in pricing of critical components. It just makes it so much harder to bring down that upfront investment to reduce capex and opex. All of which, as I'll show you now, can be traced back to the materials that go into electrolyzers themselves. So let's look at one of these electrolyzers. Let's take the example of proton exchange membrane water electrolyzers, the PEM. And when we look at the cost breakdown, it can be broken into stack components and balance of plant. When we look at the stack components, which is the heart of the electrolyzer, precious metals and coatings alone can make up between 20 to 40% of the stack's cost. That means the catalyst coated membranes, the protective coatings for bipolar plates, porous transport layers, gas diffusion layers, and other components all can use precious metals and other metals worth thousands of dollars per kilogram. That means any volatility in these material prices, supply instability, or availability can directly affect the affordability of green hydrogen. And here's the kicker. The supply chain for a lot of these critical materials are highly concentrated. If we look at the global production of minerals and metals, and I'm looking out examples of the materials that are crucial to the energy transition, the top 3 or 4 countries dominate mining and exploration of precious metals, platinum group metals, rare earths, graphite, copper, battery metals, etc. But when we factor in refining capacity, China dominates 60% or more of most of these value chains. And so that means the catalysts and the coatings for the electrolyzers are all coming from a very concentrated source. And this isn't just a hydrogen problem. The same minerals and materials are in high demand for EVs, batteries, and other energy transition applications. And the competition for supply is only going to get more fierce. But here's the tension. The faster we try to scale up that green hydrogen production to reach those milestones, the more we're likely to hit constraints in manufacturing capacity, likely due to material supply. So for the rest of today's webinar, we're not here to debate which electrolyzer technology to pick, which is the most efficient. We are looking at the minerals and materials inside them to give you a clear picture of the risk those minerals create for the future deployment of green hydrogen. So to do that, we need to map those minerals and metals in a structured way. And that's where our raw materials criticality framework comes in. The framework is a quantitative tool to help you understand which materials are critical to that green hydrogen technology and how to de-risk the supply of those materials. It's not that complicated. It's a simple 2x2 framework. And here's an example of one that we built for the PEM water electrolyzer. You can see the different minerals and metals that are mapped on the framework. To understand them, let's look at the 2 axes. On the y-axis, we have supply risk. And the supply risk is a measure of the resiliency of a material supply chain based on its geographical spread and the stability of that producing nation. Meaning that the metric tells us how concentrated the supply of that material is and how geopolitically stable it is to work with that country. Is it a country that has high rates of corruption? Is it difficult to do business with them? And so this metric gives us a zone of high supply risk and a zone of low supply risk. So for your material sourcing strategy, you should source materials essentially from more diversified sources. You want to be in that low supply risk zone. Otherwise, your technology strategy can be delayed or even blocked in the future. The x-axis is the metric for criticality. And the criticality value is the measure of a given material's total projected requirement for that technology by 2050, divided by the material's annual global supply. Again, that gives us 2 zones, a zone of low criticality and a zone of high criticality. And a score of 1 means that the entire world's supply is needed to meet the amount of that material for that application or that technology between now and 2050. Essentially, to simplify it, criticality is a metric that gives you a magnitude of the problem. So if an electrolyzer technology has a material with a criticality score approaching 1 or greater than 1, that means it becomes harder to source that material for that technology between now and 2050. Again, a higher criticality can even delay or even block your technology deployment. So this framework doesn't just tell us which materials are at risk. It's backed by data that tells us where those risks arise from and how severe is that risk. So what can you do with this framework? Well, a framework is only as good as it directs you to some potential actions. And so we're going to discuss some innovation strategies here that will help you manage those critical materials for your technology and de-risk their supply chain. I'll play out some examples in the next few slides. To do that, let's take a stepwise approach. We're going to start with each electrolyzer technology, map the key materials for that technology on our criticality framework. The materials will show up in one of these 4 quadrants. In step 2, we're going to use one of these 4 innovation strategies: novel sourcing, materials optimization, finding alternative materials, or recycling and circularity as an innovation strategy. I want to mention right up front, each of these innovation strategies is part of a toolkit for you to deploy. They're not mutually exclusive, meaning each quadrant could have more than one of these innovation strategies. It all depends on the technology and the product that you're trying to develop. So let's dive right into it. Let's take the example of an emerging technology, the solid oxide water electrolyzer. It's an emerging, highly efficient, low carbon technology for hydrogen production. But as you can see, when we map the materials that are crucial to this technology, a lot of these materials end up in a zone of high supply volatility, particularly the rare earths and silicon. Rare earths especially are what the catalysts are made of, which allow for high temperature operations, which makes the technology highly efficient. However, it's this reliance on these rare earths that make the solid oxide water electrolyzer a little more vulnerable, as these materials are refined and sourced primarily from China. So these materials in this zone of supply volatility could limit the deployment of the technology. So what are your options to de-risk the scaling up of solid oxide water electrolysis if this technology is core to your decarbonization framework? Well, that brings me to my first innovation strategy, that is novel sources. Novel sources is finding materials outside of traditional value chains like mining and refining value chains. That is looking at waste sources, unconventional deposits, or entirely new extraction environments. Let's take a look at some of these examples. Coal ash is becoming a highly researched source of rare earths. There's several companies in the US, Australia, and Europe that are now targeting the extraction and refining of heavy and light rare earths from carbonaceous waste like fly ash or industrial waste. You can look for these minerals in completely new environments. Deep sea mining, although a highly controversial topic, a lot of deep sea mining companies have received a lot of funding in the last few years to explore the seabed for minerals. And some of these resources have an average of 3 to 5x more rare earths and battery metals than those locked on land-based ores. You can also look at other waste streams like industrial wastewaters that might contain metals. Let's look at now at another electrolyzer technology, a more mature technology like alkaline electrolyzers. It's a technology that's widely deployed. It's a relatively low-cost technology. You can see that most of the minerals needed for the deployment of this technology are not in a zone of very high risk. However, it's a less efficient technology, meaning that you'd use a lot more materials per stack to produce the same amount of hydrogen than, say, PEM or solid oxide. So for every gigawatt of installed capacity, alkaline systems consume anywhere between 800 to 1,200 tons of nickel. So while these materials might be in that long-term zone of stability, its mineral usage is high for this technology. And let's just take nickel for an example. The demand for nickel is already being pulled in all sorts of different directions, for EVs, for grid storage, for wind turbine, for steel production. So if alkaline is core to your decarbonization strategy or your green hydrogen strategy, it will strain supply in the future. In the next few years, you can imagine nickel moving further to the right as demand from these other applications increase, its criticality goes up, or nickel can move further up in supply risk, as over 55% of nickel comes directly from Indonesia, largely from Chinese-based refiners. So if alkaline is part of your future growth of hydrogen strategy, nickel could limit its future deployment. And that gets me to my second strategy, which is materials optimization. That is doing more with less. This isn't just about substituting materials. It's about squeezing out more performance from every gram of material that you're using. We've seen material developers and OEMs that are turning to approaches like additive manufacturing, 3D printing catalysts, and bipolar plates by precisely controlling the geometry and thickness of the coatings that they're producing and reducing the defects on things like catalyst-coated membranes or gas diffusion layers. There are several startups and now corporates as well that are focusing on lowering loading of catalysts and coatings altogether with new material combinations. And they're trying to do that without losing any catalytic activity, which is crucial to maintain that long-term competitiveness of alkaline technology. And finally, manufacturers are moving to things like AI-driven process control with the aim of optimizing material usage. But sometimes optimization of materials alone can't solve a supply problem. When a material is simply too scarce or too risky, you just have to replace it. And that brings me to our third electrolyzer, the proton exchange membrane water electrolyzer. The technology is a leading contender in the race to meet green hydrogen milestones because it's efficient, it's highly responsive, but it also relies on really large amounts of metals, precious metals like iridium and platinum, some of the scarcest metals on Earth. The world annually mines about 6 to 8 tons of iridium, yet by 2050, in that net zero scenario, PEM demand alone will require 50 tons of iridium. So these minerals could be growth limiting to the widespread adoption of PEM technology. And thrifting or lowering loadings can only free up iridium and platinum for a couple of gigawatts of installed capacity. Clearly, we can't optimize our way around this kind of shortfall. You have to replace these metals. And that brings me to the third strategy, which is around alternative materials, that is finding substitutions for high risk, high criticality inputs with something that's more available, that's more sustainable and scalable. As chemicals and materials developers, you have to think of ways to move away from these precious metals and rare earths to more abundant metals. We are seeing electrochemists at large companies work with materials discovery platforms to find new material combinations that avoid precious metals and rare earths altogether. You can avoid using precious metals for different structural elements as well. Think of bipolar plates and porous transport layers. There are companies that are now developing graphite and carbon fiber-based materials, polymer-based composites for bipolar plates, for porous transport layers, all with the aim to remove their reliance from precious metals while maintaining things like conductivity and corrosion resistance. And finally, you can just avoid this technology altogether if precious metals are going to be a limiting factor. Replacing materials can take years of R&D. Even these new material discovery platforms are still pretty, they're still early stage. So while you're planning an alternative material strategy, how do you stave off risk from impending shortages in the next 3 to 5 to 10 years? Let's use the example of an emerging electrolyzer technology, and that's the anion exchange membrane electrolyzer. This is a technology that is vying to compete with PEM, as it avoids precious metals and rare earths, and also compete with traditional alkaline technologies. So if AEMs become widespread in deployment, they can also need massive amounts of materials in the future. And for such an electrolyzer where materials are moving closer to that criticality of 1, secondary sourcing could play a strong role in the near term. And that brings me to my fourth strategy, which is around recycling and circularity, that is designing systems and supply chains to recover materials and at the end of their useful life and put them directly back into production. So if you're an OEM that's designing and manufacturing these stacks, think of establishing recycling services. You might be a Bosch or a Johnson Matthey that's integrating recovery services, pairing your product sales or leasing models with return and recycling programs so that materials flow back directly into your supply chain. Think of designing for circularity. Make it easier to disassemble these systems to get to break down the stack and separate those high value materials without damaging them. And then finally, you can also improve feedstock collection, a pretty crucial part if you're going to recycle materials. So you should implement this framework to assess your material supply risk and then use one of these strategies or a mixture of these strategies to course correct accordingly for your green hydrogen strategy in the future. These innovation strategies can have different implications for different companies. Remember how I'd mentioned that these innovation strategies are not mutually exclusive? Well, if your electrolyzer technology has materials that are in a high supply risk or a high criticality zone, which can limit or stall growth in the short term, you might look at materials optimization and recycling and circularity options in the near to midterm as an innovation approach, with the long-term vision of finding alternative materials to replace these high criticality metals. If you're operating a technology which has materials in this zone of really high supply volatility, look for novel resources. Look for novel resources to source and supplement these materials, or invest in recycling so you can hold on to those critical materials within your value chain. And finally, if you're looking at commodity metals in that zone of low to medium supply risk and criticality, these materials don't require urgent innovation strategies to secure supply today, but they still benefit from materials optimization to reduce costs or circularity to improve sustainability profiles. In other words, don't ignore them. You just approach them with an efficiency mindset rather than a crisis mindset. And talking about crisis, remember the peak phosphate crisis that I had introduced initially? Well, we found a way to stave off that crisis. We innovated our way out of it. We deployed optimization approaches, strategies to improve agricultural efficiency with precision farming and controlled release fertilizer. We recycled phosphorus from waste streams, industrial waste streams, and municipal waste streams. And we're also exploring alternative materials through biofertilizers and novel approaches like algae and microbial solutions to reduce the need for phosphorus altogether. The phosphate story over here shows us that even when resources look like they're heading towards a crisis, innovation in sourcing, substitution, recycling can buy time, stabilize supply. And that's exactly the approach I want you to take when you're thinking about critical minerals for your green hydrogen strategy. Finally, I want to wrap up with a couple of key takeaways. I've been stressing upon this first point quite a bit throughout the conversation. Access to materials is going to be decisive. So don't make your technology approach over-reliant on specific materials, particularly precious metals. Electrochemists, specialty materials developers, look at ways that you can lower criticality of these materials and replace those high criticality materials in the future. If you're in new business development, M&A focus, or even advising government policy, think of ways that you can diversify your resources. Find novel feedstocks to supplement your supply and insulate from those global sourcing shocks. And don't think of it just for those high criticality or high supply risk materials. Today's low criticality materials could become tomorrow's bottlenecks. So as materials get pulled into multiple directions, in this case, metals for the energy transition, think of ways you can de-risk by novel sourcing. And then if you're an energy company, and this is one of my favorite takeaways over here, is that you can actually leapfrog all these material supply limitations. Focus on the next generation of hydrogen technologies, the 2.0 solutions that could completely avoid these supply constraints and maybe become winners in the future. Great. Thank you for your time. I'm happy to take some questions.
Thank you, Abhirab. Fantastic. A lot of eye-opening data and insights from the presentation today. We will now be taking questions that you may have on the presentation, the audience. You can type those into the questions box. And if we do not get to your question on the call, someone from Lux will be in touch after the webinar. We do have at least a couple in the queue. I think we'll have time for two. The first one is about your point around material substitution. So for high-risk materials like iridium or lanthanum, what's the realistic timeline and technical readiness for viable alternative materials in electrolyzers?
Yeah, that's a good question. There's a lot of R&D and investment, both at the corporate level and several startups that have been successfully lowering the amount of materials, so the loadings or optimizing materials requirement for these precious metals that are used as coatings, catalysts, etc. They've also increased their scale up of manufacturing as well. But we're still around like 20, 30%, 40% lowering loadings in that. So there's a lot of way to go in terms of just on the lowering loadings or finding materials optimization opportunities. Replacing these materials is an altogether big challenge. You've seen several precious metals companies like Johnson Matthey, Harris, Denora that are building these electrolyzer stacks and components for both electrolyzers and fuel cells. They're trying to partner with those materials discovery companies to find replacements altogether. I don't expect a true replacement in the short term at all. It's very tough to mimic the catalytic activity, the durability of these precious metals whose their job is to provide robustness and performance. So it's very difficult to find that combination. And so I don't expect anything in the short term of like 3 to 5 years. Maybe in a slightly longer term, we expect to see more materials that are tested in longer durations and then scaled up. So I'd say at least 5 years would be a reasonable timeline.
Yeah, good. Thank you. Let's do one more. One topic that's near and dear to my heart: policy. Someone in the audience asked, do you expect policies like the Critical Raw Materials Act in the EU, Inflation Reduction Act in the US, and then more recently Trump administration's executive orders to meaningfully de-risk electrolyzer supply chains, or will industry need to move fast on its own?
Yeah, that's a tricky one. I think these acts and the policies have definitely helped in funding new technologies. We've seen a wave of momentum both from the government side and a little bit on the corporate end or industrial end as well, to start commercializing new research, new technologies. But I think industry needs to start taking a little more risk over here if you're going to reap the rewards in the future. We saw $1 billion in funding that came into critical minerals specifically to extract rare earths from fly ash, one of the examples that I had mentioned. So there is opportunity where we're likely to see some new winners emerge with the help of policy, but those that are taking risk to kind of integrate new mining and refining supply chains in regions that haven't been doing this for the last 20, 30, 40 years. And it's not just on the mining refining side. You can also think of like recycling to manufacturing value chains. That's another area where we see a lot of activity, and not just for electrolyzers, like the example that I gave of Johnson Matthey over there, where they are recycling about 60% of all their precious metals back into their electrolyzer technologies. That's a great example on the electrolyzer end, but we need to be thinking slightly broader for other energy transition applications as well, and not just on green hydrogen. So yeah, I think it's going to take time. There's funding from the government, which is helping today, but we might also need things like future contract guarantees from the government as well to make these kind of investments attractive for companies to get into the mining space, where permitting and building these mines takes 10, 15, 20 years. And we're already seeing that. The Department of Defense, for example, took a stake in MP Materials, which is a rare earth miner and refiner. We've never seen that happen in the West, particularly in the US in the past. So it's going to take time, but the foundation needs to be built soon for any kind of meaningful onshoring if we want to hit those timelines by the end of the decade.
Good. Thank you for taking those two questions. And unfortunately, we won't have time for the rest of those, but the slide presentation and recording from the webinar will be sent to all attendees via your email. And after leaving the webinar, you'll be asked to complete a survey on today's presentation. We would appreciate any feedback you have to help inform and improve our future webinars. So please take a moment and check out the upcoming webinars, and we hope to see you attending those soon. Thanks for joining us. Have a great day.